Okay, so we are going to do these questions in a way that it will help you for your assessment 3, okay? So this will, as I have mentioned, this will cover everything that we have done so far, including this week topic, the magnetic properties. So the first question, I want you guys to give me the answers. What is the first ionization energy of a chemical element? First ionization, what do we mean by that? First, ionization energy. Ionization energy, as the word says, you should know that. What that means? Energy needed to remove the first electron from the atom. So we know at the outermost shells, we can give electrons and that the elements can become positive ions, isn't it? So that, so here, energy needed to give one or else the first electron from an element. We call that the first ionization energy. Are we good? What do we mean by the what is the name that we give to chemical bond formed between a metal and a non-metal? So we discuss about metallic bonds, ionic bonds, covalent bonds. So what name we give to this these bonds where we have a bond between a metal and a non-metal? For example, if we say sodium and chlorine, sodium chloride. What bond we have here? Ionic. So why we call that ionic? So they are formed in between a metal and a non-metal. Sodium is a metal and chlorine is a non-metal. So what is happening here? There, sodium will give one electron to chlorine and chlorine will become chloride ion, and then that will make the sodium chloride. Am I right? So that is giving electrons and accepting electrons. It's not sharing electrons. So when it is happening, we call that ionic bond. And that is happening between the metal and a non-metal. Any questions so far? Any question? What do we mean by a covalent bond? That is for ionic, yes, giving electrons and accepting electrons. So here what they do in covalent bonding, what is happening is they share electrons. They share electrons, am I right? So they share. So for example, CH4. So carbon has 4 electrons at the outermost shell, am I right? And hydrogen has 1 electron. So carbon and hydrogen will share electrons. So hydrogen is stable and also carbon is stable with 8 electrons at sharing with the hydrogen. Am I right? So this kind of electron sharing, the bond happening by sharing electrons, that we call covalent bond. So this is an example. So ionic bond, this is an example. Any questions so far? Yes, CH4, this methane. So that is this one. An example, it is just an example, okay? Any question? Can you do this one for me, please, if you have finished? We all know how to write the electron configurations. To write the electron configuration, we need to know the atomic number. If you don't know the atomic number, if it's not given to you, from where we can find the atomic number for different elements? from the periodic table. When you look at the periodic table, sodium atomic number is 11 and bromine is 35. You can check it if you want to. And that atomic number is the number of protons, same as the number of electrons. So there are 11 electrons in sodium. So how we write the electron configuration for this one? So we write like this. I'll give you a few minutes for you to do this. It's going like this. Am I right? So 1s, how many electrons can keep? S can keep 2. How many electrons P can keep? 6. So it's going like this, am I right? So 2p6 and 3s, how many in 3s? Or now we have already filled 10. So to become 11, 3s can hold only 1, am I right? If we have done it right, when you count the number of electrons here, it should be equals to 11. Do we have 11 when we count it? Can you write for the boron, please? How many electrons can D hold? 10. 3s2, then it's going like this. 3p6, 4s2, am I right? And we have 3d10, now 30, isn't it? Then 4p 5, is that right? So when I count the number here, do we get 35? Yeah. Okay, so you can rearrange this. Can we do that? So 4 shells, the front number says the shell number. So we can keep the shells together. So number 2 together. 3s2, 3p6, 3d10. Then we can write the 4s2, 4p5. So we can keep the shells together. Is that right? Have I done anything wrong? Now you can, whenever we have a long electron configuration, we can make it shorter. So how can we make it shorter? So you can see when you consider up to here, up to this third shell is fully filled. Am I right? Is that right? Third shell is fully filled. So that means instead of writing whole thing, you can write the third row. Shell number is represented by the row number, isn't it? So third row, this is up to here. If you consider this configuration, that's belong to the third row, the last element that we have as a noble gas. So that is argon, is that right? So you can write it like this as well. Anyone have a periodic table? Is it argon? I think it is argon. So this is up to here. As the third shell is fully filled, you can either write like this as well. So if you write like this or that should be okay. Any question up to here? So there is two exceptions when you're writing electron configuration. Do you remember? I told you guys, you can follow this pattern, this method for all the elements except two rows. Sorry, two columns. Which two columns? Copper column and the chromium column. Do you remember that? Remember or not? So you need to check, okay? Try to write the copper and chromium at home and write it and check it. Try to write it following this pattern. There is an exception. So you find it, and if you can't, find that one out, let me know. I explained this in, I think, few times. But if you still can't understand that, let me know, okay? But I want you guys to try first, because otherwise, again, you will forget. If you do it by yourself, you will remember that. Okay, chromium and copper. Whole copper column and whole chromium column is different. All the other things are like this. So can I move to the next question? Are you all okay? Next question. Determine the Miller index for the given direction and planes below. So we only have two planes. Okay, so can you tell me what's the first step that we need to do here? Axes, yes. So when you do the axes for planes, the plane should not cut the origin. Do you remember that? So you need to find the origin in a way that it's not on the plane. So the given origin is fine for us, isn't it? Because that origin is not on the plane. So then you need to put the X, Y, and Z axes. So how do you recognize which one is what? You use the right hand rule. When you turn your fingers from X to Y, thumb should direct the Z. So you can't have, like, in case if you want to put this one, if you want to change this one, in case if you want to do that, if you want to make this to X and this to Y, then what should be the Z? Take your right hand and turn from X to Y. Before you were turning like this. Now you're turning like that. So your Z should be, if you want to put your axes like this, your Z should be downward. Am I right? But what's that? So we'll use the other way around. It doesn't matter which direction you put, as long as that it will fulfill the right hand rule. So I'll keep this one Z, this one X, and this one Y. Okay, next step is what? What do you do next? You find the intercepts, isn't it? So you find the intercept. So where this is your plane. So where it is intercepting x-axis, is it intercepting or not? Sometimes it's go parallel. In that case, it will be infinite. But in this case, the plane is intercepting x at 1. Am I right? How about y? Y intercepting at this point, isn't it? So that will half. Z is at 1. Now, what is the next step? You take the reciprocal. Do we do the reciprocal for directions? No, we do the reciprocal thing, flipping thing only for the planes. Okay, so then you take the 1 over the value like this. So we have 1, 2, and 1. What is the next step? You need to check whether we have any fractions. In case if we have fractions, we need to get rid of the denominator by multiplying by a number, isn't it? So they all should be integers. Now, which brackets we should put for a plane? Square or parentheses? Which one? Square or parentheses? Which one? Parentheses. Yes, this one, the normal brackets, isn't it? Do we put commas in between numbers? No. If we have a negative minus value, where should I put the negative sign? On top of the number, yes. Any question? Are we good? Can you do this one now? So they have given you the origin, but you can have your origin in a place where it is not in a way that it won't cut it won't be on the plane. However, as they have given you the 0, you can now define your axes. It's okay to have, like, as long as it fulfill the right hand rule, you can have your axes as whatever the way that you want. So I can have them like this. Can I have them like this? So x, y, and it is fulfilling the right hand rule. Can I do like this? Can I do like this? If I do x and y like this, where should be the z? Down or up? X to y, y to x. X to y, thumb is upward. So this is z, isn't it? So you can put them in a way that it will follow the right hand rule. So this way or the previous way that I have put. So now tell me where they are intercepting, x, y, and z. X is intercepting where? -1. Y? 1. Z? 1. So next step is taking the reciprocal. Am I right? Then you have -1, 1 and 1. We don't have any fractions. So we put the negative sign on top of the number and we write it like this with no commas. Parenthesis because it is a plane. If it is a direction, we use the square brackets. Are we good? Okay, so that covers first topic and the second topic. Yes, yes. If you want to do this one y, you want to do this one y, and this one x. You can, in that case, you may need to put this one this way.
Yeah, that's what.
Yes, yes, you can. You can, but when you are putting the z, you have to make this one to x and this one to y so that you have z upward. Yes, you can do that. If you do like that, you will be having 1, 1, 1. There is nothing wrong in this because yes, still be a right answer. Yes, depending on how you define it, how you define your axes. So you need to show your axes in the exam. If you need to do that, you need to show that the axes. Any question? In case if you have the origin on the plane, what we'll do? What you do? So for example, let's take an example. So you have something like this. So I'm taking this as my x, y, and z. I want to do this plane. If I keep like this, and if I do this, what will happen? I have 0. So if you flip, when you flip the 0, when you take the 1 over the value, it will become infinite. So it's not giving us a good answer, isn't it? We can't do like that. So what we do, we can either shift the origin. So you can shift the origin to somewhere like here, if you want to, so that you have x, y like this. What's that? You can do like this. So your origin was here before, now you have shifted origin upward. Otherwise, you can shift the plane parallelly. So you can shift the origin like this so that you can find the intercept. So when you find the intercept for this one, if you move the origin, what will happen? X is what? X will never This is your X, this is your Y. X will never cut, isn't it? So the plane is parallel to X. It will never cut. And how about Y? Y is same, never cuts. Am I right? He said he's cutting at -1. Do you agree? Agree or not?
Yeah.
So when you flip it, what will happen? 1 over infinite, 1 over infinite, 1 negative 1 over 1. So will become 0, 0, -1. Am I right? So you can write it like this. Am I right? Any question? If you don't flip, if you don't shift the origin, if you don't want to shift the origin, what else you can do? What else you can do? You shift the plane instead of shifting the origin. So you can shift the plane parallelly upward like this. You keep your origin here. So in that case, what will happen? Again, X is infinite, Y is infinite, Z is 1. So when you flip it, you get 0, 0, 1. So this sounds also right. This is right as well, depending on what you do. So you have to first check where the origin is when you are dealing with planes. The origin should not be on the plane, okay? All good? Any question? This question was not in your sample. I just took it to explain you. And this is all cubes, and you should know how to do it in hexagons as well. We already did that. Okay, so let's move to the third question, third case. An element has an atomic radius of this. This is the atomic radius. The element is, most of the questions, element will be given to you, whether it is magnesium, sodium, or whatever, because it is asking you to find the density here. So you need to know the element, otherwise, like, they are saying it is FCC, Kristen. What do we mean by FCC? Face-centered cube, and they're asking you to calculate the volume of atoms in the unit cell. So how many atoms are in the unit cell for a FCC? 4. So there are 8 corners. Every corner has 1/8 of atom, and there are 6 faces. Every face has half of atoms. So altogether there are 4 atoms, isn't it? So how do you find the volume of atoms? So volume of atoms, that will be 4 atoms times volume of a sphere, isn't it? Atom is a sphere. So how do you find the volume of a sphere? 4 over 3 pi r cubed. So do we know the r? Yes. So can you find me the volume in nanometer cubes? So you can find it just putting the numbers in the calculator. Okay, when you find it, let me know, okay? How many, what you get for the nanometer cubes. Is this what we get as the VS? V for volume, S for solid. Solid parts are the atoms. Do you all get the same? Okay, so how do you find the volume of the cell? So it is a cubic cell, it's a cube. So how do you find the volume of a cube? If you know this one side, the volume of the cube is equals to A cube, isn't it? So do we know one side here? A face-centered has atoms like this, isn't it? So this diagonal is how many radius are there? 4. So you can find the relationship, but it's given in your equation sheet as well, but it's not hard to find. So if you apply Pythagoras theorem for this one, this triangle here, 4r squared is equals to a squared plus a squared, isn't it? So that will be 2a squared is equals to 4r squared. So a is equals to 4r over root 2. So you know this. So you can find a cube. So a cube is equals to 4r over root 2 to the power 3. So that will be your Vs. So can you find me Vs as well, please? Sorry, Vc, volume of the cube. That's for ACC, sorry, FCC. We did it like this. We did it with the sheet says the same thing, isn't it? Sheet says the same thing. What they have done, they have made this 4 to 2 times 2 r, and you have root 2. So this will cancel out and you get 2 root 2 r cube, isn't it? Sorry, r. Is that right? There is nothing different. Both the same. Am I right? They're both the same, isn't it? Yes. You can cancel the denominator root 2 by a denominator, sorry, by root 2 at the top. It's the same thing. So what do you get as the answer? How many nanometer cubes? Do we all get that? So we need this. If we know this too, volume of the solids and volume of the cube, do we all get 0.16? Then what? What do you get? What did you get? 0.14. Oh, can't be that big. 0.3. 0.0. It should be more than 1. 0.15 or 16. 0.16. Okay, so this is right. Okay, now when you know the Vs or the volume of atoms and volume of the cube, you can find atomic packing factor. Can we find the atomic packing factor? What do we mean by atomic packing factor? Yes, nanometer. Sorry, nanometer cubes. It deleted, I think, when I delete the number. Sorry. Okay, so what do we mean by atomic packing factor, guys? What do we mean by atomic packing factor? Volume filled by atoms divided by the volume of the cube. You already found this once, am I right? So you can find this, which is 0.74 for FCC normally. Am I right? It should be the number. So that means 74% is filled with atoms, rest is empty. Am I right? 68? Are these numbers right? If your numbers are right, you should get 0.74. Do we get 0.74 or not? Point? 76? Yeah, that should be fine. The exact value should be 74, but because we rounded up, we didn't took all this out, like, you know, the all numbers. So this is 76, that's fine. It should be 74 if we have done the calculations and took all the decimals. But we just took 2 decimals. That's why it's a bit different. That should be fine. Are we all good? Any question?
For the unit cell volume, because no matter, I cannot get the same answer using both of the equations. What are the equations and what does the R mean? Is the R the all of the radiuses? So 4.
Just one radius. R is just one radius.
Just one radius.
Yes. R is the radius. What you get?
I got 0.15, 1.3. None of them is matching. Oh,
You need to cube this. You need to cube this. You need to cube this. You need to cube this one thing. One side is that's right. So this need to be cubed. Okay, so even this is this 4 times over the I of cube. This one need to be
also technically with things that you're talking about the wrong number. They only say it's cube, so accurate it's a different volume.
Okay, you're not finding it. You're finding it. A is just, this is A. So the volume is A. We are giving you the relationship between A and R.
Yeah. I just understand why it's
Okay. Any other question? Okay, so this one, mechanical properties of materials. Sorry. Yes. I forgot the theoretical density. Can you please find the equation from the density is mass divided by the volume. So do you have the density equation, theoretical density equation? Can you tell me? Number of atoms times the atomic weight, am I right? Divided by, what's that? VC times Avogadro number, isn't it? Na. Okay, you can just put the numbers here. N is 4 number of atoms. This one, depending on the element, if it is magnesium, you can find them. But in the question, they haven't given us the element. So element should be given to you to find the atomic weight. But if you search the atomic radius, I think this is for krypton. So you can find the atomic weight if you really want to by Google searching. However, if you get a question like this, they should give you the element, what it is. So you can find the atomic weight from the periodic table. Am I right? In the periodic table, for any element, you have something at the at the top and at the bottom. At the top, you have atomic number. At the bottom, you have atomic weight. So you can find them. So this is not given. But this one is given, am I right? Avogadro number is 6.022 times 10 to the 23. We found it. This is known. So you can find the density. However, here we can't find it without knowing the atomic weight. Okay. Are we good? What's that?
0.11 or 0.16.
Get 0.76, isn't it? It should be 0.74, but we ignored all the other decimals. We just kept 2 decimals. What do you get? Do you get 0.66? 68? Not 76? 68 is right for BCC, but for FCC we should get. Can you check your calculations again, please? Are these numbers right? Are they right?
Yeah. If you put them into like, if you don't, if you take 0.74.
Okay, yes, please. So we should not round them to, they are very tiny values. So this should be, the answer should be 0.74. Because we rounded, maybe you get different values. So we already know BCC 0.68, FCC it is 0.74. So we should get that right values if you, when you put all the decimals. Okay. So because of that rounding up, we get different values. But if you have all the, if you keep all the numbers, you should get 0.74. Okay. All good. So can you go to this question? You remember this? We did the practical as well in this one. So what the question says? A cylindrical specimen of steel alloy. This is the length, initial length L naught, and the diameter, initial diameter is given to us, is pulled in tension. The stress strain diagram is given below. So what do we mean by stress? Stress is what? Force divided by the initial area. Yes. So strain means what? We use this epsilon for strain. Strain means what? What is strain, guys? Change in the length divided by the original length. So what are the units for the strain? No units. Stress, what is the unit for stress? Yes, pascals or newtons divided by meter squared. So it can be pascals, megapascals, gigapascals, or whatever it is. Okay, so now what they are asking you to do. So they are first asking you to find the modulus of elasticity. So what do we mean by the modulus of elasticity? Stress over strain, that's right, up to where? So stress over strain is not a constant throughout the curve. It is a constant up to where? Up to the proportional limit here, isn't it? So what do? You take the rise over the run. You can consider any point along the straight line. Okay, so maybe we use the E for Young's modulus. So 1,400 divided by what? So 0.0035, agree? Roughly, as long as you show your working outs on the graph, it should, if it is slightly different, that should be fine. So what are the units? Because the bottom part, denominator doesn't have any units. Numerator has megapascal. So what do we get? We can make it to gigapascals because it's a very, like, you know, what do you get here? What is it? 1,400 divided by 0.0035.
400.
400 megapascals.
No, 400,000 megapascals.
Okay, 400 gigapascals. Do we all get that? Any questions? So for this part, what we can say, so this part, stress is proportional to the strain. So it obeys the Hooke's law. So we can say stress is equal to Young's modulus times the strain. That will be true only for this proportional limit. Are we right? We already know those things. Do we? Okay, so we know the answer for the first question, which is 400 gigapascals. Next question. The yield strength at a strain offset of 0.002. Clearly indicate your working outs on the diagram. So what do we mean by offset? Yield point is what? What do we mean by the yield point? Yeah, so you find the yield point, offset yield point, by drawing a parallel line at where the x-axis is 0.002. So you draw a parallel line to this line, and where it cuts the curve, that will be your offset yield. So this is your yield point. This is the yield stress, and this corresponding strain is your yield strain. So what do we mean by the yield point? What is happening to the material at the yield point? What is the importance of knowing the yield point? Yes, your material will transfer from elastic to plastic. So below the yield point, the material behave elastic. That means whenever you take the load out, material will go back to its original size. But after the yield point, what will happen? For example, if we consider this particular point after the yield point, what will happen? When you take the force out, it is going like this, parallel to this line. So my line is not parallel to this one. So you need to draw a parallel line where it cuts the x-axis. This is the permanent deformation. This strain is related to the permanent deformation part. The recovery part is only up to here. So this can be recovered, and this is permanently deformed. So if you know the strain, you can find how much of permanent deformation there and how much of recovery is there. Does that make sense? Any question? We have discussed these things over a week. So every topic has a week to study. So it's hard to study everything in 2 hours. But you guys need to go back and read the things if you have forgotten, okay? Are we good? Any question? Up to the magnetic properties, I think. However, you will get to this week. Yes, check with Abbas, okay? So, what topics are included. But in the sample exam, you have all the topics to the end for all 12 weeks. But we are not going to do all the questions today. However, you check the topics, okay, to know which topics are included. Okay, so we know the yield point. So yield stress is 1,800 megapascals. You all agree with that? Agree? Okay. Next question, the maximum load that the material can sustain, that this specimen can sustain. So they're asking the load. Load means the force. So we don't know the force here. We know the stress and the strain. So what is the relationship between stress and force? Stress is what? Yes, so stress is equals to force divided by the area. Am I right? So if you want to find the force, force is equals to stress times the original area. Am I right? So they are asking you to find the maximum load, maximum force, where the maximum force is happening. Wherever you have the maximum stress, that will be your maximum force. Agree? So where is the maximum stress? If you look at the diagram given, what is the maximum stress? Yes, 2,300. So 2,300 times the area. So do we know the area of the specimen? We don't know, but we can find it. Can we? We know the diameter. So if you know the diameter, the area is equals to pi d squared over 4, which is d, you need to make it to meters. So that will be 0.008 squared over 4. So you can find the area. So if you know the area and this stress, maximum stress, you can find the maximum force. So can you guys find me the maximum force or the maximum load, please?
Oh, yeah.
What do we get for the area?
5.
5.
5 times 12 minus 5.
Do we all get this? Okay, so what is your maximum load now? So if you look at the load, that will be maximum force, or the maximum load is 2,300 megapascals. So you can make it to pascals by 10 to the 6, am I right? Times 5 times 10 to the negative 5. So your answer will be in newtons. So what do we get in newtons? What do you get?
There you go. And you get that
100 and 115.
115,000.
Okay, so you can say it in, like, keep it in newtons, or else you can say 115 kilonewtons, whatever the way you want, okay? Are we good? So that is the maximum load that sample can, or the specimen can take. If we can't apply more than that, it will crack. Okay, so any question for mechanical properties? There are other things that we discuss about mechanical properties. When we did the mechanical property topic, what are the other things we discuss about this graph? We discuss about where is the fracture point? Yes, end of the curve, that will be your fracture point. Modulus of resilience. Do you remember the modulus of resilience? How do we find the modulus of resilience? What's that? What is it? Area under the curve up to the yield point. Do you remember that? Modulus of resilience is the area under the curve up to the yield point. So that is this area. Am I right? So we have a easy way to, or else we have an approximation way to find this. So it is not a triangle, but we can make it to a triangle, and we can find the area of this triangle that will give you the modulus of resilience. Remember that? So you can't expect the same questions in the exam, okay? There can be any question which have been taught. So the modulus of resilience is the area under the curve up to the yield point. You can find it with the yield stress and the yield strain. And also, like, you can use E as well if you want to. If you don't want to use this, you can use this and stress and the Young's modulus to find it. It's an approximation way of finding the modulus of resilience. So it's you get two different answers depending on whether you are using stress and strain or stress and modulus of elasticity to find it. Okay, what else we know? Area under the whole curve. What do you mean by toughness? So those things you need to go through, okay? So you have them in the notes. Please find out how to find the toughness, how we find the ductility, percentage elongation, ductility. So these ones are not covered in this question, but you already know. I want you guys to go through that. Okay, phase diagrams.
You don't put your work out in the view.
Oh, I have to check with that. You have to write it down in your like.
No, I've got it there.
Okay. Okay, so in the phase diagram. So phase diagrams, I hope you remember the topic. So here we have with the temperature, with different compositions of metals. Here we have two materials, element A and element B. So here you have 100% of element A, and here we have 100% of element B. Am I right? And you can see the percentages here. So for example, here we have 50-50, 50A and 50% B. Here we have 60% of A and 40% of B. So they are in different compositions. So when we have different compositions, we can find out at a certain temperature whether we have a liquid or a solid or a liquid solid interface. Am I right? So for example, if I ask you to find with the alloy where you have 70% of A at the degrees of 1600 degrees Celsius, is it a liquid or a solid or what it is? How can we find it? 70% of A and at 1600 degrees Celsius. How do you find that? So 70% of A is where? Here, isn't it? 30% B, 70% A. So you draw a line here. So where it is 1600, so that is here. So what do we have? Do we have a liquid, solid, or a what? Liquid. So if I say at 600 degrees Celsius, what do we have? It's a solid, but it has two different solid phases. So that is solid. So alpha and beta both. How about at this 1200? Liquid and a solid phase, alpha solid phase and a liquid. So you can find what it is. So this is a eutectic system. Why I call it a eutectic system? There is a eutectic point. So which one is the eutectic point? Point Y. Why we call it a eutectic point? When you cool down, liquid is becoming a solid without having a solid liquid interface. Or else you can say when you heat up, the solid will becoming a liquid without having a liquid solid interface. Am I right? Okay, so those are general stuff. Now they are asking us to find the melting temperature of element A and B. So, what is the melting temperature of A? Yes, so A 100% is here. So that will be 1400 degrees Celsius. How about for B? Yeah, maybe, yes, 1600 degrees Celsius. So we know A is 1400 degrees Celsius and B is 1600 degrees Celsius. Are we good? Any question? No questions? Now they are talking about the phase composition at X. So where is the point X? Point X is here. So point X consists of two solids. Am I right? So in this one, in generally, when you consider alpha and beta together, it has alpha and beta together, it has 20% of B and 80% of A. Agree? Now, what do we mean by phase compositions? Phase composition means inside the alpha phase, how many percentage is B, how much percentage is A? Inside the beta phase, how much percentage is A and how much percentage is B? So how do we find that? Anyone remember? You draw a horizontal line here, am I right? Where it cuts the alpha phase here. So this is the phase composition of alpha. So how do you write this? In this one, what do you have? 10% of B and 90% of A. Does that make sense? How about the beta composition in the beta phase? Okay, so in the beta, you have 95% of beta B and 5% of A. Do you understand what it means? In the alpha phase, that is right. But when you combine all together, both alpha and beta together, and if you have the average composition, this will be your average composition. Does that make sense? Any question? Any question? No questions? Next one. Weight composition, sorry, phase fractions or the weight fractions. So how do we find, what do we mean by that? What do we mean by weight fractions? So when you consider the point X, you have alpha and beta both. Am I right? Inside the alpha phase, if you consider inside the alpha phase, you have 10% of B and 80% of A. Inside the beta phase, you have 95% of B and 5% of A. That we have found already these ones. But when you add these two together, you can say the average composition is 20% of B and 80% of A. So we know these stuff so far. Am I right? That's what we have found so far. Is that right? Yeah. Now what they ask, the weight percentage, what that means. If you consider this, how much percentage is alpha and how much percentage is beta? So this is the weight percentage of alpha and weight percentage of beta. Yes. So it's the same on 10 and 90. Oh, 10 and 90. Sorry. Yes, it should be 100. Yes. Okay, so how do we find the weight percentage here? Weight fraction. How much of alpha is there? How much of beta solid is there? So how much weight percentage you have? You use the lever rule. Do you remember that? Using the lever rule. So what you do here? Anyone remember how to do this? If I find the weight percentage of alpha, for example, alpha is this line, the alpha line is this one. You look at the opposite side, isn't it? You look at this line here. So the length of this line, that's why it is, we call it lever rule. You look at the opposite side. So that line, length of that line is what? 95 minus 20, or else you can, am I right? 95 minus 20. And then you divide by this total length. This is the total length, isn't it? So that total length is 95 minus 10. So you make it to a percentage that will give you the weight percentage of alpha. Is it clear? When you do the, can you do me the beta, weight percentage of beta? So how do we write the weight percentage of beta? This distance, am I right? This is 20 minus 10 divided by the whole distance, which is 95 divided minus 10 times 100%. So can you find me these two numbers, please? What we get?
This one,
So this is 88% and this should be 12%. Am I right? So when you add, if you have done your calculations right, when you add both together, that should be 100%, isn't it? If 88% is alpha, then the beta should be 12%. Is that right? Okay, yeah. So this is, when you consider this alpha, sorry, X here, 88% is alpha and 12% is beta. Inside this alpha phase, you have this percentages of A and B. Inside the beta phase, you have this composition of A and B. Am I right? Do you understand what we have done? Any question? No questions? Okay, so that's, we have done this part as well. Last part in this question. What is the point Y? What do we call that point Y? Eutectic point, and we know what is the meaning of eutectic. Okay. So any question regarding the phase diagrams? What's that? Point Y is the eutectic point. We already discussed. Point Y, where the material will become liquid to solid and solid to liquid without having interface. So this point here. Eutectic. 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 Any other questions? So what else you need to know? Okay, now let's if I say you this, if I ask you this for the phase diagrams. So they were referring to point X. In case, sorry, can you tell me this as well to know whether you have understood this correctly? If they were referring to a point somewhere here, what will happen? Point somewhere here. And if they ask the same questions, what are the phases that you have here? Alpha and liquid, isn't it? So when you do your, when you draw this line, you have alpha here and you have L here. So you have Cl and C alpha, isn't it? Not B alpha and beta. So depending on what so you are touching the liquidous line here and you are touching a solidus line here. So this is a liquid solid interface. You do the calculations in the same way, but instead of having beta, now you have L. Does that make sense? Okay. So let's move on. Next question is on electrical properties, isn't it? Yes. A current. So we know the current. It's an axial direction through a diameter. So you have a cylinder like this, and current is flowing like this. And the length is given to you. Current density, J. Current density, how do we find the current density? You have an equation in the equation sheet. Current divided by the area. So amps per meter squared. So what is the current? 0.225. And the area, it's a cylinder. And it is a circular area, isn't it? Am I right? So you can find the area, which is pi d squared over 4. So you find the area and divide that by the area. So I put a note here, okay? This capital A stands for amps. It's a unit, and this A note is the area. What do we get? You need to convert the millimeters to meters again, okay? What do we get for J?
1300, 257.
What's that?
Huh? Yes.
Is this what you have? Okay, so any questions? Next one. If the voltage measured between 2 points separated by 30 millimeters is 16 volts, determine the electrical resistivity of the silicon specimen. So they are asking about the resistivity. Do you remember what is resistivity? It is a material property. Resistivity is equals to resistance times what? Then we did the practical last week. Area divided by length. Is this right? Can you check your equation sheet, please? Yeah. Okay, so you can find the resistivity if you know the resistance, area, and the L. So do we know the area? We know that. Length, do we know that? Yes, it is 30 millimeters. Do we know the resistance? We don't know, but we can find it. To find the resistance, we know in electrical circuits, V is equals to IR, Ohm's law. Am I right? So you can find the resistance if you know the voltage and the current. Voltage is given to you. Current is given at the top in the question, which is 0.25. So you can find the resistance in ohms and you can put them here, and the resistivity is ohms meter. Do you remember this? We did it in the practical last week, yes. What do we get? That? Yes, yes. Because your area also in meters, isn't it? So this is 0.03 meters. 0 point. Is this what we get? Finished? Are we finished? Yeah. Why 1.003? 30 millimeters. Otherwise, you are right. This one is 30 millimeters. 30 millimeters, you have to 3 millimeters. That's all. Yeah. Otherwise, you are right. Okay, I'll move to the next question. Do you remember the capacitors? We discussed this last week in the lecture. Do you remember? What is a capacitor? What is a capacitor, guys? It's yes. So capacitor is a device which stores energy in an electric field. It has a metal plates, two metal plates. In between the two metal plates, you have an insulated dielectric material, insulator here. So how do we charge this? Do you remember? So when you connect this to electricity, what will happen? Electrons will flow from this end to the other end, and this plate will become positively charged, and this plate will become, this plate will become positively charged and the other plate will become negatively charged, isn't it? When it is saturated, there is no electrons will flow. So when the plate is saturated, now nothing will flow. Then what you can do, you can take this and you can connect it to something so that this will, so for example, bulb, this electrons will flow this direction, so this will light up. And it is only happening till all the electrons will flow. Okay, so that kind of a thing we call a capacitor. So it stores energy in the electric field. Why these electrons will stay? Because it is, you have an insulator between the plates, so the electrons can't move through the plates. It's only, it will get stay on the plate. So that's why it can charge and discharge. You will learn more about this charging and discharging in of capacitors, inductors, all that in electrical fundamentals. Okay, so we don't go to that extent. However, they are saying consider the parallel plate capacitor having a capacitance of capacitance like resistance for resistors. We consider the capacitance for capacitors, inductance for inductors. So this is the capacitance. Boys, are you discussing about the question? Okay. So do you need time to do the question before I explain, or do you want me to explain first and let you to do it then? Okay, so the capacitance is given to us. The area is the area of this plate. Area of this plate is given to us. So this is the area. Dielectric material position between the plates. Calculate the required plate separation. They're asking you to find this separation between the plates. And the permittivity of the electric material, dielectric material is given to you. 4 times 10 to the negative 11 farads per meters. So can you find me the equation for capacitance is equals to what? Permittivity times? Permittivity is times area divided by L, is that right? Okay, so here everything is given to you. This is given to you. This is given to you. Area is given to you. You need to just find the L. So you make the L the subject. That will be permittivity times the area divided by the capacitance. So you can find them. Am I right? You just need to rearrange the equation. So what do you get? L is the distance between the plates. 2 millimeters? Oh. Do we all get 2 millimeters? Any question? That's epsilon, which is permittivity. Can I move to the next question? Do you need more time? Done? If you have finished, you can try this one, okay? Till others finishing their work, you can try this. In meters, yes, yes. So I made it to millimeters times by 1000. Yes, you are right. Okay, next question. 0.55 meter long brass rod at 25 degrees Celsius. So you have a brass rod like this. It is in two fixed supports. So at 25 degrees Celsius, it's with no stress. Stress is 0. Find the magnitude and the type of stress that develops when it is heated up to, now you are heating it up to 89 degrees Celsius. When you heating up, what will happen to the material? It expands. Now when it's trying to expand, but this support's not allowing it to expand. So what kind of stress it is? Is it a tensile or a compressive stress? So it's trying to expand, but those supports are pushing inward, pushing inward. So is it pushing like this, or is it like pulling? Supports are pulling the material or pushing the material? What is happening with it? Pushing. So is it compression or tension? It's compressive force, isn't it? So that stress type of stress will be compression. Does that make sense? If we reduce the temperature, what will happen? If we reduce the temperature below 25, what is happening? The material want to shrink, but the supports are pulling. So it's a tension. Okay, now the next part. How do we find the stress? So they're asking to develop the stress, find the stress. Young's modulus is given to you. E is given to you 100 gigapascals. Gigapascals 10 to the 9, isn't it? And also linear thermal expansion coefficient for brass is given 20 times 10 to the negative 6 per degree Celsius. So these two are given. So they are asking you to find the stress. How do we find the stress? You remember, how do we find the stress? Stress is equals to Young's modulus times the strain. Is that right? Am I right? So Young's modulus, we already know the Young's modulus. This one is known, which is here. Strain means what? What do we mean by strain? Strain is what? Change in the length divided by original length. Okay. Now, when you look at the thermal expansion coefficient, we discussed that topic last week and we did the tutorial as well. So you guys can't forget it. It's too early to forget. So tell me, change in the length divided by the original length is equals to what? In thermal expansion coefficient, what is the relationship between linear thermal expansion coefficient and this one? Do you remember this? Do you remember this one from last week? Remember or not? Okay, now you should have them in the equation sheet as well anyway. So you can find the strain, thermal expansion coefficient times the change in the temperature. Am I right? So you can find the stress. Stress is equals to Young's modulus times linear thermal expansion coefficient times the change in the temperature. So you put the numbers in the equation and you can find the stress, which is a compressive stress, what it is. Okay, what do we get for the stress? What is stress? Stress is equals to 100 times 10 to the 9. This is given as 20 times 10 to the negative 6 times the change in the temperature 89 minus 25. What do we get, guys, when you put this in the in the calculator in pascals. What is your answer? 128 megapascals. Yes, 128 and 6 zeros. So that means 128 megapascals. Okay, so your answer is 128 megapascals. 6 zeros, it's mega. Any question? No questions? No questions?
On this, 21 or 25?
25. That is the zero, like no stress. When there is no stress, the temperature is 25. Can I move to the next question? This will be the last question that you can do. I think the other topics were not discussed yet. Yes, so we haven't done this. Yeah. Yes, we can do few more questions. Yes, we can. Okay, so this is this week topic, magnetic properties of materials. So they are saying magnetic properties, when you consider the magnetic properties, we discuss about permanent magnets and electromagnets. Here we are looking at electromagnets. I don't know whether you know this stuff because only 2 were in the lecture anyway. None of you were in the lecture. So what they say, a coil of wire which has 500 turns and 0.2 meters in length carries a current of 7 amps, and the permeability of vacuum is given to you. So the permeability of the vacuum, mu naught, is given to you. Okay, so what is happening here? So when you have a current carrying coil, what will happen? When you have a current carrying coil, that will induce a magnetic field. So that has a magnetic field. Magnetic field is represented by these lines with arrows. So these lines should not be touched with each other. So how do we know the direction of the arrow? The magnetic field, they are going from north to south. So how do we know the direction? You use the right hand rule. When you turn your fingers in the direction of the current, thumb will give you the direction of the magnetic field. So I have put it right. Am I right? So if the current is going in the opposite direction, then the flux will be in the opposite direction. Okay, so here, this is your current. And also we have number of turns. So it has number of turns of how many? 500. And this is the length. The length is given to us, am I right? Yes, this is 0.7 meters length. And also, yes, that's all they have given to you, right? The mu naught is given to you. And they are now asking, what is the magnitude of the magnetic field strength? So this field created by this current carrying coil can be found using this equation. So H is equals to, you can look at the, you can look at your equation sheet, mu times I over L, is that right? This is what you have. N. you don't have mu at all. Yes, mu. Yes, you don't have mu, and you have instead. Sorry. I also forgotten the equations now. Ni over L. Am I right? Okay, so N is the number of turns, I is the current, L is the length. Do we know everything here? So this is the externally applied magnetic field. So that field is created by this current carrying coil. So that field strength is equals to what? N is 500, I is 7 amps divided by 0.7, that will be 5,000. What is the unit here? Amps per meter. Am I right? Because you have number of turns doesn't have any units. Current is amps, L is meters. So amps per meters. Any question? This is in amps and this is in meters. This one doesn't have any units. So 5,000 amps per meter, is that right? Okay, now they are talking about the induced magnetic field. This is the flux density. So that is given by B. B is equals to mu times the H. So they are asking about the vacuum now. Whenever you have vacuum, that will be the permeability of the vacuum. So B is equals to permeability of the vacuum times the H. So permeability of the vacuum is given to us. What it is 1.257 times 10 to the negative 6 henries per meters. And you times this by 5,000. So your answer, you can keep all these units or else you can put them as Teslas. Tesla is a unit, okay? So you can use that Tesla, or otherwise it's henries, amps per meter squared, or else you can keep it as Henry. So what do we get?
6.2.
6.2? 10 to the power? Do we all get this? Any question? Okay, now what they say? Now what they say in the next part? Above nickel. So you have your current carrying coil here. We are going to do this in the practical next week. So we are putting a nickel bar here. Now in the nickel bar, there is an induced magnetic field that is equals to, that is the same B. Instead of vacuum, now you have nickel here, isn't it? So permeability of nickel times the H. So they haven't given us the permeability of nickel in the question, but they have given us relative permeability. What do we mean by relative permeability? Yes, so relative permeability of nickel is equals to permeability of nickel divided by the permeability of vacuum. So permeability of vacuum is already known, and relative permeability of nickel is given to you. So you can find this one and you can put them in, put that in the equation and you can find B. Can you do that? Yes, yes. You can print it and bring, I think. You can draw on that.
You should be able to.
All good. What do we get for B? You are finding B. You for H, yes, for H, yes, you use 5,000, isn't it? It is 5,000. Relative, yes. So this, yes, so the relative permeability is 500, and this is given to you something 1.2 something. 10 to the negative 6, isn't it? Yes. Yes, so you find that for the nickel, and you use that in the equation to find B. When you have a, you're going to do this in the practical. We have some different kind of bars. You are going to put them, and you're going to find this stuff. You're going to do this by yourself in the practical next week. Any question? So last part. Can I move to the last part? Okay, last part. This again we discussed last Tuesday, did we? So this is about magnetic susceptibility. Magnetic susceptibility is relative permeability minus 1. Do you remember? We know that now what is relative permeability. So minus 1 will be magnetic susceptibility. So magnetic susceptibility is 0 for vacuum because the relative permeability is 1. So 1 minus 1 will be 0. So that is vacuum. So if your magnetic susceptibility is a negative value, what we call that material? If it is negative, that means 1. What do we call that material? I'll ask two of you maybe. Diamagnets. So when the magnetic susceptibility is a positive but a small value. So if it is maybe 10 to the negative 2, 10 to the negative 3, if it is positive but small, what do we call that? Paramagnets. When your magnetic susceptibility is too high, maybe 10 to the 6, in the power of 10 to the 6, what we call them? Perimagnets. Ferri, isn't it? Okay, so what is the importance of these ferri and ferromagnets? We can't say them as a straight line. Do you remember? They are not straight. They are, the B and H are not straight, like, proportional. So they go like this. And when you discharge, they will go like this, and they will be like this. So we call this hysteresis loop. Do you remember? We can make permanent magnets with these materials because they have a retaining magnetism. Even there is no external field, still you have a B here, see? Because of that, they can convert to permanent magnets. And again, these ones, permanent magnets, we can divide into 2 categories, soft magnets and hard magnets. We have discussed all these things in the lecture. Unfortunately, lecture was not recorded. That recording thing was not working for 2 weeks. So if you have any question, let me know. Okay, that's all we can do because the rest of those things, we haven't done the theory yet. Optical properties, these ones are not done yet. Corrosion and electrochemical cell. We are going to do this in coming weeks. Okay.